Welcome back to The Explainer. Today, we're diving into a genuinely mind-bending duality. We're going to look at the massive collision between pure, boundless mathematical theory and the strict, unforgiving constraints of the physical universe. On one side, you have the realm of absolute abstraction, where infinity roams completely free. And on the other, you've got the hard thermodynamic reality of the physical world we actually live and compute in. Think about it. Can infinity actually exist in the physical world? In our heads or on a chalkboard, we can easily conjure up the idea of endlessness. But what happens when you try to force that abstract concept into real-world technology? What happens when a digital system demands endless resources from a universe that is strictly finite? That friction right there is exactly what we're digging into today. So, part one, the abstraction. We're looking at Cantor's mathematical infinite. To really grasp this conflict, we got to jump back to 1891 with the legendary mathematician George Cantor. Before Cantor, infinity was kind of just thought of as a potential, a process of counting that you just never finish. But Cantor, he dared to look at infinity as an actual completed mathematical object, and he proved it with a stroke of absolute genius. He published what's known as the diagonal argument. This incredibly elegant proof completely bypassed all the traditional messy dependencies to show something wild, that some infinite sets are fundamentally strictly larger than other infinite sets. Infinity isn't just one giant uniform abyss. It actually has structure, and it has scales. The mechanics of this diagonalization are actually super elegant. Imagine you could somehow create an impossibly huge, exhaustive list of all real numbers between 0 and 1. Step 1, you write them all down as infinite binary fractions. Now, step 2, you draw a line straight down the diagonal of that list, taking the first digit of the first number, the second of the second, and so on. Finally, step 3, you take that brand new diagonal sequence and you flip every single digit. If it's a 0, make it a 1. If it's a 1, make it a 0. The result? You've just birthed a completely new number that mathematically cannot be anywhere on your original list. You assumed the list was complete, but the diagonal proves it absolutely isn't. This absolutely rocked the foundations of math and philosophy. Thinkers like Ludwig Wittgenstein saw this as a performative paradox. Basically, the diagonal process generates a rule, a clear, articulable command that inherently cannot be applied to the system it describes. It's a hard structural boundary. Cantor proved that no matter how gigantically infinite your discrete list is, it's actually mathematically too small to handle the true continuous infinite. Now, looking at Cantor's actual infinite, it works perfectly, right? Because it's completely ethereal. 0 energy, 0 physical space, pure logic. But then, we slam into the hard reality of physical networks, championed by the decentralized economic theories of David Lancashire. In the physical world, every single bit of data requires matter, it requires space, and it requires thermodynamic energy to store and transmit. You simply cannot map Cantor's boundless infinity onto physical hardware without completely destroying the machine.
Which brings us to part 2, the physical wall, and what we call the blockchain tragedy.
We're pivoting from abstract math to a massive critical problem in modern technology, the illusion of the infinite permanent ledger. See, traditional decentralized systems like Bitcoin and Ethereum operate under this mathematically and physically flawed assumption that a database can just grow endlessly forever. Users pay a tiny one-time fee to drop data on the chain, but the network nodes are expected to store that data until the end of time. It's a textbook tragedy of the commons. The protocol is basically socializing the compounding thermodynamic cost of eternal storage, just hoping volunteer nodes will shoulder the massive weight of an infinite ledger. Just look at how misaligned the incentives are in those traditional models. In regular proof of work or proof of stake, the network only pays for solving arbitrary math puzzles or locking up capital. It pays literally 0 for the physical work of actually routing the data. It relies entirely on a volunteer system, and, well, what happens when you ask volunteers to infinitely store petabytes of data for free? You get a massive free rider problem. Nodes quit, the network bloats, and eventually the whole thing centralizes around a few giant corporate data centers. But check out Saito's proof of transaction at the bottom. This actually introduces real network sustainability because it finally pays for that physical data routing.
Let's get into part 3, the thermodynamic reality of Saito.
David Lancashire recognized early on that you absolutely cannot build a boundless digital environment on finite physical infrastructure without eventually running out of resources. So, he developed an economic framework that actually forces the network to obey the finite physical limits of the universe. Instead of paying for abstract hashing, Saito introduces proof of transaction, or POT, This mechanism measures and pays for the literal physical work of moving data from point A to point B. Every time a transaction is passed along, the routing node cryptographically signs it, and here's the brilliant part. That routing work value decays mathematically with every single hop it takes. Why? To heavily encourage nodes to build direct, hyper-efficient physical connections, rather than routing data through clunky, centralized bottlenecks.
But how do you actually solve the infinite storage problem? Well, through a mechanism called automatic transaction rebroadcasting, or ATR. ATR is Saito's primary thermodynamic constraint. It totally tosses out the myth of a permanent eternal ledger. Instead, it treats the blockchain as a transient, finite data layer. It strictly aligns the physical cost of storing data on a hard drive with the economic cost the user actually has to pay. And this ties directly into network security with the golden ticket pay split. When a block is produced, the reward doesn't just get dumped on a miner. It's split 50-50. Half goes to the miners solving the hashing puzzle, and the other half goes to a randomly selected routing node from the active transaction path. It's a fantastic alignment of incentives. Miners and routing nodes are economically forced to cooperate. The network is secured by rewarding the actual delivery of value to users, completely sidestepping those predatory monopolies.
So, practically speaking, how does a finite ledger actually function day to day? It's really neat. The blockchain has a strictly finite circular length. If your data slips past the active history window, but you want it to stay on-chain, it has to pay a rebroadcast fee to be included in a new block. If your transaction has enough unspent crypto attached to it, the network automatically grabs the fee and carries your data forward. But, and here is the brutal thermodynamic reality check, if those funds run dry, your data is ruthlessly pruned from the ledger. Poof, gone. The fantasy of digital eternity gets replaced by sustainable, real-world physics.
Which brings us to our final section, Part 4, the epistemological synthesis. We've covered abstract 19th century math and hard modern network economics. So what's the grand underlying thread connecting them? It really all comes down to the profound symmetry of structural limits. Cantor proved the logical limit. He showed us that mathematically, a discrete, countable list is inherently way too small to contain the infinite continuum. And Lancashire proves the physical limit. He shows us that any physical decentralized network is inherently too small to store an endless infinite stream of data. Both of these guys realize that when you try to force the infinite into a rigid system, whether it's a conceptual list or a literal hard drive, the system simply breaks down. And that boils down to this absolutely crucial point. Structure is defined by its limits. Cantor used his diagonal slash to define the limits of the countable, and in doing so, he built a functional reality for transfinite set theory. Lancashire uses the economic cost of data storage to define the limits of the decentralized ledger, building a functional, sustainable reality for Web3 infrastructure. Bottom line, without limits, there is no structure. There is only collapse. Which leaves us with a pretty heavy question to chew on. As we keep building these massive, increasingly complex tech environments, what other supposedly infinite digital systems are out there right now, quietly collapsing under their own thermodynamic weight because we refuse to acknowledge their physical limits? Definitely something to think about. Thanks so much for joining this explainer, and keep questioning those limits.